Good evening, all. Welcome to live session number 10 for Computational Fluid Dynamics of Incompressible Flows. In this particular course, we have been discussing on several topics from the beginning. We started out with the governing equations for governing equations for fluid mechanics, and then we classified different kinds of PDEs as parabolic, hyperbolic, and elliptic equations, and we discussed finite difference method to solve this set of equations under different kinds of boundary conditions. We also analyzed how to evaluate the stability criteria for a given algorithm that you can develop using von Neumann method. And subsequently, we extended the technique from diffusion problems, and then we went into convection, and eventually we solved the Mach algorithm where we solved the complete Navier-Stokes equations. So that was what we were covering up until last week. So now from this week, we will discuss another method called finite volume method. So, and within the finite volume method, we'll again follow the same sequence. So we'll initially start with elliptic equations, or we'll just start with the diffusion equation this week. And then we'll directly go to convection equations. The methodology will be very similar to what we were doing in the case of finite difference method. So first we'll start the steady heat conduction equation, unsteady heat conduction equation, and then we will discuss convection schemes, and then we will eventually see how to include pressure and solve for incompressible cases. As we were discussing even in the Mach algorithm, the problem is we have three variables u, v, p that we are trying to solve, but then we have only the momentum equation which has the time derivative with respect to v and v, but we do not have any explicit equation for doing the time marching for pressure. So we need to come up with some kind of different scheme to solve that particular problem, and that is what we will discuss towards the end of the last week. That is a simple algorithm, and then there are other advances of that which you can pick up from here. But this will be the basic one, that the idea will be very similar to whatever we did in the Mach algorithm. This week we will start with this finite volume method. So we'll say what is finite volume method and how is it different from finite difference method. And then just like in finite difference, we were doing different kinds of uh, stencils. So we have first order, second order accurate methods, and so we have some way to determine the order of accuracy where we were using Taylor tables. So similarly here we will understand what is the order of accuracy for the particular scheme you have chosen. So we have two things that we need to worry about. One is the mean value and gradient approximation, which we will discuss in this week. Followed by that, we will see how to do the discretization using this particular formulation for diffusion equation under steady and unsteady conditions. Then we will discuss some of the MCQ questions, which will be very similar to the ones that you can expect in case you're appearing for the exam. And if the time permits, we will also see how to kind of implement this in code for 1D, 2D steady conduction equations on rectangular kits. And I'll present this way slightly different from finite difference method that we were doing previously, where we were kind of doing a structured mesh. So we'll not solve the problem in an unstructured mesh, but I'll kind of give you an idea of how this thing gets implemented if you have to extend it to unstructured grids. If time permits, we will do that towards maybe by April 12th, like towards the end of this course. And then finally, again, before if time permits, we also discussed about a multi-grid solver for Poisson equations. So we already discussed about Gauss-Seidel, Jacobi method, direct method, several methods we already discussed previously on how to solve the Poisson equations. So of those iterative methods, we will take up Gauss-Seidel method, and we already know that it takes a little more time to solve using Gauss-Seidel. We will understand what is one of the reasons for why this particular Gauss-Seidel can be slow for Poisson equations and what can be done to kind of accelerate that. One of the solvers that is used is a multi-grid solver. This is used in if you are using OpenFOAM or any other thing, you already have these things built in, even in Fluent also. So we will discuss what is the main idea behind this multi-grid solver, the intuition behind that. We will see a implementation of that in Julia, and then we will conclude this week's session. To start with, the idea of finite volume method is in finite difference, what we were doing is we assume that we have a function phi. Let's say we are solving some equation. Let's say phi is a variable that we are trying to solve for, and then we need to estimate del phi, del x, etc. So this we were doing using an approximation like pi plus 1 minus pi minus 1 by 2 delta x or so on. So if I have a 1D grid, so hi, good evening. So we have a given domain, we were discretizing it a given number of points, and then from there we are estimating finite differences, the derivative using finite difference form. So in finite volume, what we have is we have control volume, similar to control volume approach. We divided it into a certain number of grid points, or maybe I'll take a 2D one, so it will be straightforward. So if we start from a 2D grid, so this is my domain. It doesn't have to be rectangular. So if this is a cell of my interest, the notation is similar to what we were using before. The current cell will use the capital P is the current cell that we are interested in, and then the neighboring points, north, south, east, and west. And for all the phase centers, we use the small letters, east, west, north, and south. So any governing equation, let's take it as normal equations for a steady state diffusion equation. If you are starting with that, it is something of the form, you do not have any unsteady term, or let's say even if you have an unsteady term, so the general equation is del del t of rho p. So this is the unsteady term, and we have an advection term, diffusion term, and then a source term. So this is general equation. And unlike the finite difference formulation, we will be using the conservative form. So this particular form is called a conservative form. You can also write for, of course, for incompressible flows, you can usually write this as, and this was the form we were using before. So the same term we were replacing with rho u dot del times p. This was the one we were using in the finite difference form. There also you can also start with this equation and do the finite difference scheme for this also. But for this we will use this form because the difference between finite difference and this particular one is here we will consider a small, like just like the previous one, but then we will actually do the integration. Let's say we'll start with the simple form like this, where you take these terms, some del dot j is some source term. Let's take a simplified version of this, where j is basically rho u bar p minus gamma del p. If I have an equation like this, then if you take a control volume around this particular one, if I integrate across that small volume, so now we can use the Gauss divergence theorem and then convert this into whatever is this surface. Across this surface, we will do the integration. So this will be only on the surface. This remains the same. So the major difference is in the previous finite difference method, what we were doing is the same equation. What we were doing, let's take if you take this equation. So in, let's say this is a 2D problem. So this will be del j like you have jx jy equals to some sp equation. Like we will first write something like this, and then we will make an approximation for del j del x as jx at I plus 1 j minus jx at I minus 1 comma j by 2 delta x, and similarly for the other term. So this is the finite difference formulation where again it's the same code, like it is the same cell that we are considering. The only difference is this is a difference form, but now we'll be using an integral formulation. So what the main advantage that we can get here is when we do something like this, we need the grid to be aligned with whatever direction we are taking the derivatives, and also we need the function to be differentiable in the first place. So if your particular domain, like if the particular problem that you're solving has some discontinuities where the derivative does not exist, then this formulation might, like you cannot just use this formulation. Let's say you have a shock wave or something that you want to model. There is a sharp discontinuity across the wavefront. Then this might not exist. Like it will be very problem will actually become very stiff and you might not be able to solve. But if you were to use an integral formulation where we are doing an integration like this, we do not need it to be like the strict form in this sense. Of course, we have to make some assumptions about this to simplify this further and then convert it into set of algebraic equations. That is what we will see now. So this is the main difference. So this is the differential form versus the integral form. So just like the ones if you are familiar with, this is very similar to the control volume method that we use in thermodynamics, etc. That we have even in the fluid mechanics. So now the next step is again this is some kind of integration. So we need to convert this into set of algebraic equations, and then we can use whatever methods that we learned before, say Gauss seidel, whatever that is. So we have to convert this into something of the form Ax equal to b, for which we need to make some assumptions. So that's where the next thing comes. So that there are two kinds of integrals here: one a volume integral, and then we have a surface integral. And then there are other terms, as in we also need to find out, say this j is basically the term that is here. So this has two terms. This is the advection term, and then you have a diffusion term. Within the diffusion, I have a gradient that I need to calculate or estimate. And then here there is a u times phi. This is the advection term that we have. So broadly speaking, so we need to deal about the time derivative, which for now we'll keep aside. And then we need to worry about this gradient, how to estimate gradient, like how to convert this gradient in some form that can be used with Ax equal to b when we want to convert into like this. And then we need to deal with advection. So this week we'll only worry about how to get this gradient and how to deal with this source term. So this is the first one we'll take up, and this is the second one we'll take up. Next week we will discuss about different convection schemes and how to kind of treat this term u bar times p. This will be very similar to what we were doing in case of hyperbolic equations when we did the FDM method. So it will be very similar to that one. So we can find analogies from there. So first we'll start with the source term. So we have to convert this into some form that so that we will be able to solve for it. Let's say even otherwise also if u is constant, let's say even in hyperbola, let's say we already know the velocity and we are solving for some other scalar transport variable. Let's say we know the flow field already and we need to only solve for the temperature field. So in that particular case, P will be my temperature and U is something that is already specified to us. Then in order to solve that kind of problem, still we need to find out how to do this integration with P inside. So how to do that is we have to approximate something like this, some term, some function P across the control volume of that particular P. Then how do we do this is again we will use the same expansion. So let's say let's start with a simple 1D problem. So this is my P and some notation. So let's say this is my delta x. I'm just showing for 1D, but it just stays for other problems also. So there is some origin somewhere. So the distance till this point is xp, xe, xw, and let's say we are interested in finding the value of p at any given point. So if I want to do this integration, I need to have p as a function of x. So this is that particular x that we are worried about. So across this control volume, if I were to do the integration, this will be from xw to xc p of x dx because it is 1D problem. So this will be, again we can use the Taylor expansion around the point P. So P of xp is 1D problem. So I can write something like this. Let's x minus xp square and so on. And this we have to do the integration. So we have not assumed that it is a uniform grid or any such assumptions are not made here. All we are saying is this particular has the dimension delta x. So that will come here. So I can write xp as xw as xp minus, I don't even have to make that. So I'll just write something like this. This will be some constant. Let's say phi p is the value of p at the point P. Just do the integration also. So have phi p times xe minus xw plus an integration here. Del phi del x is evaluated at point P, so this will be independent of dx. So that will come out e phi dx. And then I have x minus xp whole square by 2 if I substitute the limits. and then I have all the other terms. So here I'll have some cube by 3 times delta x. So this will be something of order delta x square, because I have a, leave this part for now. I'll just write something like this. So what would be this term? Xc minus xw is the length of this, plus what can we say about this? To have xc plus xw minus 2xp times c minus xw by 2, plus the higher order terms, which are of delta x square. So let's just write that thing like that. So as long as you maintain this condition that xp is the midpoint of along that particular whatever cell we have considered, if you can take the point P in such a way that it corresponds to centroid, of course it is in 1D, if you extend it to 2D or even in 3D, as long as we take a point P close to the centroid of that particular element that we are considering, this term will actually go to 0, and then the approximation is basically like something like this. So across any cell, if you do an integration of the quantity, you can approximate it just with something like this, and that will be second order accurate. And here we did not make any assumption as to whether delta x has to be same across the cells. So this is only one cell I have taken. I did not assume that delta x is constant or something like that. All we are saying is the point P has to be taken such that it is at the center of the cell that we are considering. As long as that is satisfied, we will get this second order accurate approximation for the any functions. Like I just wrote p of x here, but in general it can be any source term. Let's say I have a source term q something as x cube or something, and if you want to do an approximation of this integral across my element, this will be basically at that particular between xc plus 2. So this will have xc plus xb by 2 whole cube times delta x. So this is the approximation we will be making for that particular function. This is with respect to the mean value. So the source term is kind of handled in this particular fashion. Now we also have another term is with respect to the gradient. Let's say we have del dot j times dv. So this is the divergence term that we will be dealing with. So we use the Gauss divergence theorem and then we convert it into some surface js dot ds across the surface, whatever control surface we are having. So in 1D case, what would this boil down to is I'll just have, these are my control, instead of a surface we have just these two boundaries. These are my boundaries for the control volume that I'm considering. So all we are doing is we'll just simplify this as summation across all the boundaries. So that will become, so just like what we did, this integration again, the same, if we do the Taylor series expansion here in the same fashion, we'll get the same thing again. So JE times whatever is the area of that SC plus West times SW. Like it is a 1D problem. If it is a 2D problem, then we'll have the other terms also with respect to the north term and south term, etc. will be there. But this is also just like the previous one. This is also a second order accurate scheme. As long as we are making sure that the values of this J flux that we are taken at the centers of the phases. So if I have a domain, so if this is my phase center, east, just so on. So there will be flux across this phase. So all we are doing is like when we are doing this integration, what we have to do is we have to integrate across this surface, this entire surface. So the approximation here is we are only taking the value at the center of the face of each face. Like if you have an arbitrary surface, so let's say you have something like this. So for each face center, you'll have to take the corresponding value of j at that face centers and then multiply with that with the corresponding area. Let's say this is extending out or into the domain. So that particular area you'll multiply with the flux at the corresponding center values. That will give me the integration of this value. So this is a gradient approximation that we'll be using. Even otherwise, let's say there is other gradient that you can take, which we'll see in final. So these are the two terms that we have in our diffusion equation, and then there is an unstudied term. We'll see little later. But for now, one is this flux, how to deal with the flux, and then the other one is with respect to the source term. So even to simply even understand this intuitively, is the idea is we have something that is generated within this control volume. Whatever is generated within the control volume under steady conditions should be leaving from the surfaces. So if we combine these two equations, so we have Je dot Sc is the flux that is leaving from the east surface, this particular term, plus Jw dot Sw is the flux that is leaving from the west surface, should be equal to whatever that is being generated, that we already have whatever is the S, the source term calculated at that particular point P times delta X. So this is the generation term, should be equal to whatever is leaving from the either sides. This is for a 1D case. If you have a 2D problem, it will be very similar. So whatever you are generating from this point P should leave from all the four surfaces. For any arbitrary surface, it's the similar again. First calculate the centroid, store everything at the centroid, calculate the flux from each and every phase. Whatever is generated here should be flowing out of the entire surface. Then what are these SCSWs are basically the areas of each element that we are considering here. Again, for a structured grid, it will be constant. For unstructured grid, you have to keep log of all these values. We'll see that also in one example today. Now the main point for this week is we'll only start with just like how we did with finite difference. We'll first start with a conduction or a diffusion equation. So still we have something of this sort. I will just take something like this. This is the diffusion equation, and what we are trying to do is use finite volume method for this. So again, we'll start with the 2D case. So just some notation is we'll take the full equation and then do it. It's not from here. So first thing is how do we convert this? Is let's take this cell, this particular cell, do an integration for that cell. What would happen to this equation? So this is basically del dot del phi dv. This we can use the mean value approximation that we just derived. So this is C SPP times whatever is the volume of that cell. So this is basically delta x times delta y. This is delta x and this is delta y. And this is just similar to what this is my J term. This is the flux term that we are having. So del dot J. So all I have to do now is to convert it into surface integral del phi dot ds bar, where my surface is along this line. And how do I do this thing? As I said, we'll have to do calculate this at the phase centers across the entire surface, whatever how many ever phases we have, and then do a summation of that. So this will give me del phi on the east. So on the east surface, because it is aligned with the axis, so this will just be the gradient along phi, like there won't be anything along the y direction. That will be del phi del x on the east face times the area of this east face is delta y. So this will be the area, and direction is I cap. So this is a one outward direction. So I have delta y. Now on the north face, I'll have similarly del phi del y. The area is delta x. On the west face, the area is along the negative direction. So I'll have a minus del phi del x. And similarly on the south face, I'll have minus del phi del y. Now we need to approximate these things, which we already know from our finite difference schemes. And how can we do this? Del phi del x on the east face is basically phi e minus pp. by delta x. This is again second order accurate because we are using both the forward and the back, like the central scheme. So this is second order accurate, and so on. Similarly for the other terms. So for the north term, this will be phi n minus pp. Similarly, the other terms here. So phi west minus pp. We have phi south minus pp. Sorry, this will be delta x. So now we can group the terms together. So the general form for all these finite volume methods will eventually give us something of this form. So I can collect all the terms for phi p, and the coefficient is ap. We have some coefficient for phi east, west, north, and south, plus some constant term. So this constant term is basically the source term that we have, and then we have all these terms together. So what are these terms for the east phase? It will be something as delta y by delta x. Similarly for the west phase also it will be similar. North and south it will be reverse. Reverse in the sense the reciprocal of that. And then AP is the summation of all these things. So I'll just write that as sigma A and B. And B is the neighboring points. So you just add up all the coefficients of these points, and then I'll be able to get the values of AP. Now, whenever we have, so the first thing is this is with respect to the discretization within the domain. Now we have to deal with the boundary points. So let's say if I have to solve with this particular boundary, I know again we have three different conditions. Let's say Dirichlet is straightforward. So I have a domain something like this. So this is a cell that is sharing one of its faces with the boundary where the value is specified. Let's say that is the phi boundary value. So what happens now is the flux that we are calculating. So the equation is AP phi p is A east P east, or maybe I'll just write for 1D case. Then you can easily extend it to other problems also. So this is my 1D case. So this is my boundary phi b, and this is my point P. This is my face east. This is the west face basically, which is the boundary. So in case of 1D problem, so AP phi p for all the interior cells, the equation goes like this: A east P east plus A west P west plus some source term B. So the moment we have a boundary, so let's say in this case, the west face is the boundary. So phi west is the quantity that is known to us. So what happens is A, E, phi E, this is an unknown, plus this entire thing will go into the source term. So the A west will remain the same times phi B plus B. So this will be my constant term that I need to solve for. And what will happen to AP? Will it still be AE plus AW? So you can quickly solve this here. So you have the equation is still the same: del phi del x on the east face minus del phi del x on the west face times that whatever the area is. Let's say A is the area that we are considering, should be the source term. Del phi del x on the east face is so here what we have for the west face is phi west is phi boundary, is a quantity that we already know. So the term for phi p is the half a 1 by delta x. Sorry. plus 1 by delta y is P is times 1 by delta x plus the source term. So which is what we have. So Dirichlet is straightforward. All we are doing is the corresponding condition here is now added into the source term. So when we write the code, we have to just make sure that the source term B should include the term that will be coming from the flux that is already coming from the side which is in contact with the boundary. Now if we have a Neumann condition, so there what we have is del phi del x on the west face is 0. So all that happens is this particular term will go to 0. So I'll have phi e minus pp by delta x times area. This entire term will go to 0. So half pp times 1 by delta x as. So you can see the source term is having one from the generation and another term coming from the flux. So in case of Neumann condition, we do not have any flux that is coming from the boundary. So source term only has B remains as like the normal B that you would get without the source term. I'll just call B prime and nothing else. So this will be just SP times V. A east will remain the same. A west will become 0 whenever we have 0 flux. And then AP will basically be A east plus A west. This still applies. The only thing that is changed is the value of AWS becomes 0. And then we have mixed BC that will also be similar to this one. So whenever you have mixed BC, it will have a flux plus another condition. So same applies. We use the mixed BC also. Where let's say you have A times del phi del x plus some B times P is some constant. There's some condition like this. And what will happen? Times P equals to C. So we can approximate this again. And we can use this back in the original equation. Pp by delta x minus so again the same remains. So just like Neumann BC, we'll have Pp then some term somewhere. I think I missed some term somewhere. Okay, just a second. So we have del phi del x, which is Pe minus Pp by delta x minus P boundary minus Pp by delta x times A into something like this, where the flux on this boundary is calculated as Pb minus Pp by half cell delta x by 2 Sp times V. Usually we will not be given Pb, we will actually be given something else. So something like this. That will be the problem. Okay. And then now we have to approximate B in it. So we have Cp times 1 by delta x plus 2 by delta x 1 by delta x times P east, and then I have a source term plus some constant. So this constant will be the one that will be coming from my equation, where this is like the Dirichlet one. I think I have made a mistake here, so this was the mistake. You have noted it down. So I have a delta x by 2 here. So this will be the Dirichlet one equation. We'll do the mixed one also now. Just to clarify, so there was a mistake here when I was doing the Dirichlet condition. So the derivative is taken between B and P. So it will be Pb minus Pp by half cell width. That is delta x by 2. Accordingly, everything will change. So this will be the one that you should be using for Dirichlet. Neumann remains the same. We'll do the mixed condition also. So for mixed boundary condition, we have say the example for mixed boundary is the heat transfer coefficient. So you usually be given del phi del x on the boundary plus some constant. See, so this will be the mixed boundary condition, something like this. So we have del phi del x, the total flux that is leaving from the east phase minus total flux that is leaving from the west phase should be the source term times some constant. This will be V by A. So let's say this will remain the same, P east minus Pp minus, you can do with the ghost cell or we'll do the normal way. So Pb minus Pp by delta x by 2. This is one way to go about it. But the one that I used is something like this, where you'll directly approximate this with T minus B times Pb by A. So if I do this approximation, then all I'll have to do is Tp will have a 1 by delta x term, P will have a 1 by delta x term, and then I have everything else combined into my source term. Did you miss something here? So when we have a purely Neumann condition, B will be equal to 0. So this is equal to 0. This is similar to what we have in the Neumann condition. And when we have a Dirichlet condition, pure Dirichlet condition, the other term will go to 0. So you have to just change that accordingly. So this will not work. So you have to switch to the other one. So for a mixed BC, you can replace it in this particular form. But in 2D, we'll have the other terms also. We'll have delta y term, and then we'll have north, south, etc. So if you have a 2D problem at this particular boundary, then we also have to take the cells, neighboring cells, my P cell. Then I'll also have terms coming from north and south. So I'll have to consider the fluxes that are coming from the north and south phases also. There will be some additional terms with respect to north and south. But other than that, everything else remains the same. Yeah. And coming to the unsteady term, this is also very similar to what we were doing, like just extending from the finite difference form. So the equation we have is something like this, plus some advection term, diffusion term, and then some source terms. So what we'll be doing is now we'll, in addition to whatever integration that we are doing across the control volume, now we also have to do integration across time. So that will be some t to t plus delta t. Should write it in. So I have t to t plus delta t, and then I also have a volume integral. Similarly for the other terms. So just like what we were doing in case of space, what we did is we have a domain and we are doing, like, instead of time, you can think like just like what we were doing integration in case of space. So we have some integration term, some constant phi, and then we were doing the integration for tx. So this is what we are doing in case of the space, so x to x plus delta x. And we kind of approximated this as b phi p times delta x, where phi p is the point that is a geometrical centroid for the domain that we have considered. So instead of x, now all we are doing is instead of p, we are having this rho phi, etc., and we are integrating from t to t plus delta t. So instead of p, we are having some term here, some function here times dt. This is what we are trying to approximate with. So what we have to do again similar is in just like space where we considered a center time. In time now we do not have the concept of centroid in time directly. So what we have to do is we have two time steps, t and t plus delta t. So function will go some way. So now we have to take some fraction. So just like in centroid is basically the midpoint of these 2 points. Now at some point between these two, let's say if this is fraction f, this is 1 minus f or something. So we'll have to take this fraction value for all the values. We'll have to take this kind of averaging and then get this value. So for case of centroid, f is basically 1 by 2. Depending on the value of f you choose, the scheme will change again. So f times whatever is the value of p at let's say the previous time step. So here it should be reversed. Okay. F times whatever is the value taken at the future time step plus 1 minus f times whatever the value that we can take at the previous time step. So some kind of averaging that we'll be using. So if you recall, this is something very similar to what we were doing in case of FDM. You can kind of find the analogy between this and the weight Crank also, like weight method that we were discussing in case of hyperbolic and equations also, where we were having this f where if this f is 1, then it is an explicit method. So implicit method. If f becomes 0, this is an explicit method. F becomes 1 by 2, it is Crank-Nicolson. And we can take different weights to decide the weightage of implicit versus explicit. This is what we were doing previously also. So you can find analogies between finite difference and finite volume methods. The remaining everything else remains the same. So now if this is how I integrate some function, some arbitrary thing here. So instead of phi, you will have that arbitrary function, whatever function that I'm solving for at the current time step and the previous time step. So if you have a diffusion term, so the diffusion matrix will come here. If it is a source term, the source term will come here. Advection, we'll see advection in next week. That will come accordingly. This is pretty much a summary of whatever is discussed in the lecture videos. We'll quickly go through previous year problems first, and then we'll discuss some applications of this. Finite volume method carries a physical meaning of conservation within itself. So this is the main advantage or the main difference between finite difference and finite volume methods. When we were discussing finite difference, let's say if you recall the Mach algorithm, how did we ensure continuity equation, let's say, or in general, any equation of this that we are dealing with here has something of this form. This is a general convective diffuse equation we have. So this particular form is called a conservative form. So what do I mean by conservation is, let's say I have a domain, and then let's say we have some flow happening from somewhere. So this is some inlet, and then let's say this is my outlet. Some flow is happening like this, and this is the problem that I need to solve for. So in finite difference, what we did is we kind of discretized into some grid points, and at every grid point we evaluated these derivatives. We using the Taylor table, we constructed some stencil, and then we approximated these derivatives, and then we solved for the problem completely throughout. But when we do that kind of thing, we'll have some residuals. Like each Taylor expansion has some residuals in it. So there is no way of guaranteeing the thing that we like physically. What we already know is any cell that I consider here. If I consider an arbitrary control volume here, something like this, I always need to make sure that whatever is coming in should be equal to whatever is going out plus the generation term that we have. So that is what we call, like, that is how we derived all these conservation equations. If you recall how we derived Navier-Stokes or how we derived the continuity equation, etc., we all started out with this assumption that we can choose any arbitrary size control volume, and within that control volume, we need to make sure that whatever is generated should be equal to whatever is coming in minus going out, or something like that. We already we derived all the conservation equations of that sort. But when we kind of made it into differential form, and then converted into finite difference matrix, there we are not making sure of that something of that sort is happening there. But here, so this, you make it something like this. So if you are solving this, then this is not actually called a conservative form, because you're if you're converting like this, then you have some additional terms also. You'll have some term considering this thing. This is basically which conserves your mass for incompressible flow. This term is kind of, we are assuming it to be 0, and then we are discretizing this with the finite difference form, which in finite volume what we are doing is we're actually solving this equation, and we're also using an integral formulation where the size of control volume doesn't matter. Irrespective of the size, you are still having that whatever be the grid size you take, whatever is coming in should be equal to whatever is going out if you do not have a resource term. That is what we are calling conservation. That is kind of always being maintained. Now this is different from the concept of accuracy. So even though conservation is satisfied, it doesn't mean that we are having an accurate solution. That is something different that we will see when we solve problems. Maybe in next week when we do convection, we will see, and it will be a little more clear. But for now, the idea is in finite difference, we are enforcing conservation in a slightly different way. We are still getting conservation, but it is only like accurate up to a certain order. But when we do into finite volume, we are it is kind of ensure that when we do this integral, we are making sure that it always happens. So the scheme satisfies conservation by default. There is no tolerance or anything of that particular sort. Yeah, this is again a very straightforward one. So how do I calculate the areas for each of this? So let's say the first one is A east, which is area of this one, which is delta y. I should have given this one. A east is delta y I cap, and A north is delta x j cap. Okay, this is very straightforward. Yes, in a finite volume method for a system with no sources or sinks, the sum of fluxes across the faces of all the cells in x direction is equals to. So maybe here it will be very clear what we mean by conservation. So when we were doing finite difference, we are just solving at this particular point, and we are saying here it has to maintain that whatever continuity or whatever x momentum, y momentum equations that we are solving has to be solved only at these points. Like each and every grid point that you take, that is what we are solving for. So that is what we'll be maintaining consistently, but we do not know anything that happens across. So for example, if we were using finite difference method, we cannot make sure that whatever flux coming here is equal to whatever flux that is going out there, because each cell there will be some error that can get accumulated. Eventually it will either increase or decrease. Like if you have reached the convergence, then you can kind of assure that okay, that error is within your limit, but otherwise we are that is not kind of maintained. But in finite volume, we are always making sure that this is always equal to whatever that is going here. So this equality is kind of maintained across from every cell, in which essentially means that this will be equal to the one that is living outside. If there are no sources or sinks, if there are sources, then that they are automatically accounted for. So this question says that if there are no sources or sinks, the sum of fluxes across the faces of all the cells, if I take all the cells, then that should be equal to whatever is going out minus whatever is coming in. For a uniform grid in numerical simulations, the average value of a field variable, when calculated using the mean value approximation, is second order accurate for cell center, phase center, both cell center. This also we have discussed. Yeah, though it mentions that it is a uniform grid, it doesn't have to be uniform in general. Even if it is a non-uniform grid, this kind of thing will actually get satisfied. So as long as you take the cell center, cell centroid values, then it will be second order accurate. It's actually both phase and cell centers. So one for the mean value approximation, the other one we used for something. So for the mean value approximation, we take the cell center, and for the gradients where we were using the phase center values for the flux. Both are second order accurate. Which of the following statements are true about finite volume and compared to finite difference methods? So finite volume ensures the conservation of physical quantities like mass, momentum, and energy across control volumes. We derive the finite volume equations from that, so this is true. It can handle complex shapes and unstructured grids. So this is the main advantage that we get here. So when we were deriving the equations, we were not assuming anything about the shape, but when we were deriving finite difference equations, so if I am kind of implicitly assuming that the gradients, whatever the stencil that I am creating, should be aligning with the grid. I mean, should be aligning with the geometry that we are considering. So that was the main limitation where that's why the most of the examples that we consider are rectangular, or depending on your coordinate system, we only solve rectangular problems. But now we can actually move on to complex shapes also. The shape doesn't matter anymore. So all we have to do is accordingly construct our cell and then solve it. But then there are other problems. Once we have, let's say I have a domain something like this. Say I have something like this. Then the only thing that we need to worry about now is, let's say this is one cell center, this is other cell center, and the face normal is somewhere, depending on which side you're referring to. So now what we need to store is in structured grids, the one that we discussed. I think we didn't discuss this up until now. Is what do we mean by unstructured grids? Is up until now, whatever course that you have seen, all I have done is I have kept a for loop, I equals to 1 to n and so on, j equals to 1 to n for 2D also. So something like this. And I'm able to access all the points just using this loop. So any grid point, I have a simple mapping that will tell me how to go to that particular grid map. And it's always like I know the connections. Like the connections are can be expressed in a very simple way. So if I'm at a given cell I know what are all the neighboring cells. I know how to move from one cell to the other cell directly, and they are kind of very straightforward. What we do in unstructured is this kind of rule. The rule that we use from moving current cell to neighboring cells is not consistent across the entire domain. Then we call that an unstructured grid. So, for example, you can have cells. For example, in some places, if a given cell will be surrounded by 4 cells. In some other places, the same given any given cell can be surrounded by 3 cells, etc. So I can have a domain like this, for example. If I extend it, so if you take this particular cell, it has 3 neighbors. If I take this particular cell, this will have like all the each side will have each face will have 1 neighbor. So this will have 4 neighbors. So I cannot use a simple scheme like this to actually move from one cell to another cell. Like in order to like general form, as I said, is we'll have to eventually solve for equation like this, where I need to know how to move across the cells. So where NB is the neighboring points. So I take any given cell, I need to know what are all the neighboring cells, and I can solve this using Gauss-Seidel method. So in Gauss-Seidel, all we have to do is assume some values for this P naught and keep updating them. This is what we were doing in Gauss-Seidel. So in order to do this in structured grids, it's just the same rule. Even if I'm here, I know that how to move across all the 4 cells. Everywhere it is the same scheme. So it will be very easy to do that. But once we move to unstructured, now we need to keep track of every cell. So we need to come up with some unique ID for each and every cell within the domain. And we also need to store how each cell is connected to every other cell. So now we need some kind of a graph structure or something that tells us, okay, if I'm at a given cell, how to move to the neighboring cells and how to get access to the values of the functions that we are trying to solve in the neighboring cells. That will be the additional overhead that we'll be adding in cases of unstructured grids. But the advantage here is infinite volume, because we do not worry about what, like as long as you have these values, you don't have to worry about anything. You have to just solve this directly, which is kind of very simple with finite volume method. The overhead is more like a computational overhead, but if from an implementation point of view, it is not any different from as if it were a structured or unstructured, it doesn't make a difference. The algorithm is straightforward. But if you want to do the same for a finite difference method, then it becomes tricky. So if you, let's say you take this example for suppose, how can I implement a finite difference formulation for this? The shape itself is complex, which is not aligned with any geometry that we can simply take. So these kind of things will require some kind of transformation wherein you can convert this into a problem where you can come up with a simple grid or a stencil, then it will become easier. So that is what the third statement says. The FDM is more flexible for irregular geometries, but it's actually not true. Finite volume is actually better for arbitrary geometries. And then comes the last one, where finite volume is better for problems involving sharp gradients and discontinuities. This is what I was saying before. In finite difference, at every point we are calculating this thing, but in finite volume method, we are doing integral across the surface. So since we are doing an integral, we do not need that to be differentiable in the first place. So that kind of course, if you are using a diffusion equation, you need to be at least first order differentiable up to first thing. So whenever there are sharp gradients or anything, finite difference cannot be directly used, but finite volume can actually be used. Which of the following assumptions is or are involved in finite volume? And to those of you who are appearing for exams, you can expect questions where multiple options are actually correct. I think someone actually asked that in the discussion forum also. So it's not like only one option can be correct, you can have multi-correct also. Which of the following assumptions is or are involved in finite volume discretization? The flux vector J bar varies linearly over each phase of the cell. The general variable vary phi linearly between the cell centroids. Actually, we used both of them in the while we are deriving the mean value approximation. We actually use these things. So what we are, how did we come up with this? Is when we did the Taylor expansion, we did this thing Vp plus. So we used a second order accurate method. So we are essentially assuming, and this is we are assuming to be Vp. This is actually linear. So if you have multiple cells, so what we are essentially doing is if these are the cell centers, multiple cell centers, this is some Vp, this is some other Vp, like P is varying in some way. Say P is a function like this. What we are doing is we are approximating this with a linear function between these two. Linear function between these two. A linear function between these two. This is what we are doing. This is what we are trying to do. So we have an actual solution which we do not know. So all we are trying to do is we are fixing some grid points and then we are assuming that the value between this and this is linear and find this corresponding heights at each and every point. So that will essentially give us, in this particular case, it will give us 4 equations that we need to solve for, and then that will give us these 4 values, the heights of these things. Okay. The discretized form of 1D unsteady diffusion equation using an implicit scheme is given by phi n plus 1 is sigma n b p n plus 1 plus a p is naught cp naught plus p. So you can see this term here. Both have n plus 1. So this is an implicit scheme where ap is ap naught plus sigma n b n b. What is the corresponding discretized form of the 1D unsteady heat conduction equation with no source term? So this is actually given to us directly from this equation. So how do we solve this problem? So maybe I'll give you 1 minute so you can quickly solve it, or maybe a couple of minutes. Yeah, are you able to figure this out? So the idea is what is so this we have phi will be replaced with t, and if it is a 1D problem, the neighboring points will be just I plus 1 and I minus 1. These will be my neighboring points. So it's an implicit equation, so it should have a plus 1, all the n plus 1 terms should be there for ti plus 1, ti minus 1. So this and this can be ruled out. And then we have on the LHS we need n plus 1, so everything has that. So coming to this term, so we need an ap naught plus sigma amp plus some source term. Source term is not there, so b will be 0. So this will be equals to I think I gave the same options. Yeah, so you can see the term here. This is the summation terms which are n plus 1, and then Pp naught which has the previous value. I should have written n, but fine. So this has an n plus 1 and this has an n. Which one should it be? So if I just write this equation, AP is basically AP naught plus sigma A and B, P and B. So this will be A naught plus AI plus 1 plus AI minus 1 times TAN plus 1 is sigma A and B is AI plus 1, TI plus 1 n plus 1, AI minus 1, TI minus 1 n plus 1 plus A naught TP is something plus source term. So these things will actually go off. So all we are left with is AI TI n plus 1 will be A plus 1 TI plus 1 n plus 1 plus AI minus 1 TI minus 1 n plus 1. And then I'll have these additional terms coming here. Sorry, there was a confusion here. So I have AP, which is basically AI TI n plus 1 is AI plus 1 TI n plus 1, AI minus 1 TI minus 1, and then I have AP naught PP naught, which is basically AP naught is basically AP minus sigma A into P and B. Sorry, sigma A and B. So AP is AI minus sigma A and B is AI minus 1 and AI plus 1 times PP naught is TIN. Yeah, sorry for the confusion. I think now this is clear. Okay, consider the one-dimensional steady-state heat conduction equation with constant thermal conductivity kappa, where del dot K delta T is 0, using finite volume method and central difference scheme on a uniform grid. Okay, sorry, this is AW. The discretized form of the equation at node P is written as APTP is AETE plus AWTW. This we already know. Assuming kappa is constant and heat spacing is uniform, what are the values of the coefficients AP, AE, and AW? So if this is constant, all we have can write this as simply del square T is 0. Central difference scheme using FEM or central difference scheme. So this will essentially give me T east plus T west equals 2 times TP. So I have AP as 2, A east as 1, A west as 1. In the finite volume method, which mathematical theorem is used to transform the volume integral of the diffusion into a surface integral? So in the derivation, we were using something like this, del dot something. It's basically surface integral. But yes, this is what we were doing. So this is basically Gauss divergence theorem. We didn't use any other ones, but fine. So this is the main one. If the discretized 2D steady diffusion equation is given by this particular term, what is the expression for AE? So, but 2D steady equation is del dot gamma del phi is minus S. So this is a steady diffusion equation with the source term. So if we do the same Gauss divergence theorem, we'll have this as I said. So you'll have summation of gamma F del phi f dot es bar, maybe I'll use a just not to confuse with the source term, is the source term times delta v. So this, if we do the integration, we'll have for each phase. So for the east phase, so this will be gamma e times del phi del x on the east phase times a east, and so on. The other terms will be there. So this will become gamma east times phi east minus phi p by delta x east times ae plus 1. So we'll have to take all the terms for phi p on the RHS. So we'll have the constant ae is basically the coefficient of phi e, which is gamma e times ae by delta xc. This is also kind of straightforward. There any questions? I don't think there are much questions in this, so this is straightforward one. Now we have some coding problems where let's start with a 1D sheet conduction problem. So I have a domain like this that I'm willing to solve for. So my equation is d square t dx square is minus some source. So this is the equation we are trying to solve for. So there is a rod or something which has some heat generation inside, and we are trying to solve this thing for different boundary conditions we can have. How do we write the code in finite difference form? So the only difference from this one and the ones that we were discussing, that we discussed in finite difference, is I added something called as sparse arrays. So if you recollect, when we kind of convert this, let's say first do this thing to finite volume formulation. So I'll have something of the sort AP TP is A east B east A west D west plus some source term. So this is the form I'll eventually end up with. And once we have this form, I can write this as a matrix. Then I'll have all my AP terms here. This will be my west, so on. So this is the kind of matrix I'll be having. So if I have n nodes, so this will be my n by n matrix. So for n nodes, I'll have to store a matrix of size n cross n. So if I have 1000 nodes, so this will be like 10 power 6. 1 million elements have to be there. Out of all the 1 million elements, most of them are actually 0. So each row will have at max 3. So essentially I'll have 3 times n minus 2 plus 2 times 2. So the first element will have 2 and the last one will have 2. So this will be 3n minus 2. So these are the elements which are not equal to 0. And then I have everything else are equal to 0. So I know that all of them are actually 0, but still I am kind of storing all of them, which are like a 10 million per 1000 nodes, which is kind of just like kind of waste in the sense that we do not have to store all of that. We already know that most of them are actually zeros. So the other way to store this matrix is something called as sparse arrays. So the trick there is instead of storing the entire matrix, what we do is only store the indices ij and the corresponding values where the element value aij is not equal to 0. So this way I have to do is store only this 3 and minus 2 elements into 3. So I'll have to store the values and I have to store the indices where the value is not equal to 0. So now I'll be storing just like I know that there are 3 and minus 2, and like that I have to store 3 arrays. So this will be 9 and minus 6. So this is of order n, like it will scale linearly, while if I'm storing the entire matrix, this will actually scale in quadratic. So this like I'll have to store 10 power 6 things here, but here only like around 10 power 5, so like 1 order reduction. So that is the main advantage with sparse arrays. Of course, the mathematics changes a little. Once I have a sparse array, then the way I solve this equation will be a little changed. We don't have to worry about all of that. All of them are already taken care of most of the solvers. So this is just to kind of tell you that this is another way to solve. I mean, another way to kind of represent your matrix. So in Julia, we have this packet sparse arrays that does the same thing. So our element size I considered as uniform grid L by n. Area is basically when we do the integration, we have this area term, the one that I've shown before. So this area we are taking as 1. And these are the ijv that I'm talking about. I comma j are the indices of the element in the given matrix that we will eventually solve for, and v is the value of that element there. So what this line says is now create an empty array which is of integers, and the last one is a float, which is actual value of the element in that particular matrix. B is where our source terms are stored. Initially, we declare it to be 0. Now all I have to do is do it along the grid, define my boundary conditions, etc. So I'll start with AP equals to 0. We know AP is summation of all the neighboring coefficients. So we'll go phase by phase. So this is a 1D problem. So we'll have only east and west phases. So for the west phase, is if I equals to 1 is the left boundary, I'm giving a Dirichlet condition. So TW is 400. So with this condition, I can calculate the coefficient, and that coefficient is Ka by delta x, which we already calculated. And I'll add that coefficient into AP. And there will be a source term that will get added to uh, this we have already seen when we are deriving the Dirichlet condition. Whenever we have a Dirichlet condition, the source term will actually get the AW times TW term. And the other end, I'm just keeping it as Neumann condition, so there is nothing that will actually go in there. So now, like these are for all other phases, except for the boundary phase. For all other phases, you just calculate the coefficient and then put that index into this. Now for the east phase, again another Dirichlet condition. So T I specified as 300, and for all other phases, you just add that to the AP values. B is basically Q times delta x. Now all I have to do is this is the operation where you do this is actually a direct method, but and you can always replace this with an Gauss Seidel or any other method of your choice. And then you can solve this to get a solution. So this will be something like this. I didn't do mesh convergence, etc. So the idea is what I was saying before. So between each 2 points, what we are doing is we're assuming that it is linear, and then you club all the points and then you get your arbitrary shape that the problem actually solves for. So the difference you can see from this method and what we were doing when we started to find a difference is only how do we do the sparse matrix operations. We know the matrix is going to be something of this sort. So instead of going I cross I, we are only looping once, that will go across the loops at any given point I. So now I need ith element, and instead of j, I'll have I minus 1 and I plus 1 that will have their corresponding coefficients that will be entered into this. So these are the coefficients. So at I minus, so for the J1 we'll have I minus 1. So this is for the west phase, which will be I minus 1. And for the east phase, that will be I plus 1. So for these two phases, I'll add the value. So I comma j will store the indices, and this v will actually have the corresponding coefficient value. This minus is just because when we write it in the matrix form, we'll essentially solve this as is basically a set of simultaneous linear equations that will be solved for. So all these things will actually have a minus in them. I think this is clear. No questions, right? Now the same thing we can extend to a 2D problem. So now it becomes a little tricky here is once we have the 2D, now we have to keep track of these indices in a slightly different way. The same problem when we are doing in 2D. Now I need to have a unique index for every cell I create. So I'm denoting with this function index I comma j, which is basically this you might already been familiar with, but again this is a structured grid, so I can simply write, as I said before, because it is a structured grid, I can simply write a function like this. But once we move to unstructured grids, then I cannot write a simple form like this, which will be applicable for all the cells. I cannot condense into a single form. So I'll have to maintain an array that at any for any given cell, all the neighboring points have to be done in a different way. Here, neighboring points is straightforward. I have an index for any given cell. I can get the neighboring cells as A and B. I can directly populate as you just calculate I minus 1, j minus 1. A and B of ith cell is basically calculate this index at I plus 1, I minus 1, j plus 1, j minus 1. So this is a straightforward one. So you don't have to worry much about it. But once we move to unstructured grids, I have to, like, I cannot use some function that can calculate all these things. I have to actually store the element values for each and every cell within the domain. So that is the additional overhead we'll get with unstructured grids, but there are other advantages with unstructured grids. It kind of reduces the number of elements that you have to take to solve for a given problem, and then for complex geometry, structured grids are not always possible. Grid may not align with the geometry always, so unstructured is the one that we naturally go to. So we'll see that extension also a little later, because we also have to deal with something else when we didn't discuss up until now what happens when the angle between this is here. You see that axis is kind of aligning with your grid points. What happens if you have some angle between them? How do you compute flux then? That is something that we didn't discuss, so I'll keep that for the next, maybe towards after 2 weeks, once we discuss simple, or once we discuss convection. I think by the end of this week, once we discuss simple, then we'll discuss that particular, how to handle this non-orthogonality, etc. So, but for now, the idea remains the same. So now we have I, j, and d. We use the actual value that will be stored. This array will store the actual values. Now we have a for loop between the entire thing. I, j will vary across the entire domain. So P is the corresponding index, like I said just now. So everything else remains the same. Now instead of two boundaries, in case of 1D, we'll be having four faces now: west, east, north, and south. So for the west face, again Dirichlet condition. East face is also Dirichlet. This is just like what we solved before. And for the north case, we'll use a Robin boundary condition, where I have a T infinity and then a heat transfer coefficient specified. When these two things are specified, then things change a little. So I'll just show how that thing is handled. Let's say this is my north boundary. So at this boundary, heat transfer coefficient is given, and then T infinity. I think I'm using a different notation. Yeah, T infinity, and this is my boundary cell TP. So this is my given cell P. So I have west, east, then I also have the south. So what we are trying to do is we are trying to estimate del phi del y at this boundary. So this is basically my north boundary. We are trying to estimate this value. So we know del phi del y is phi p minus. So we are going along the y direction, so it should have been the reverse. So it will be, instead of p, I am using p. So let's just use t. Del t del y on the north face can be written as TP minus TP by delta y by 2, and this we have the equation. So we know Q is basically minus K times del T del Y at the boundary face, and this Q is given by H times T minus T infinity. Now we can club these two equations, so that will give me, instead of T we'll have T boundary minus T infinity by K is TP minus TB by delta Y by 2. Now I have an equation here that will tell me to have a T infinity just plug these equations together. I'll just take it on RHS. So I'll have TP times 2 kappa by H delta Y is TB times 1 plus 2 by H delta Y. Then we should have inverse this. So this is the TP term, and then we have TB times I have a 1 here, plus I'll have 2K by H delta Y, and then the T infinity term. I think I changed the sign somewhere, so this will be minus TP plus TB. If I take this on RHS, you have plus here, so something like this. So TP is basically some kind of weighted average of these two quantities. That equation will actually come into this term here. where this TB term will actually go into the source term. This is just like the Dirichlet condition. And wherever we have the Neumann, so Neumann is basically the heat flux condition that will go into the corresponding coefficient, which in case of Neumann, it doesn't have anything, the zero value. So we do not have anything, but once we have a mixed condition, we'll have something into the, that should be added into the coefficient. So that will be the weight resistance that we have here. And everything else remains the same. So now here we have IP. So this P index will go into the I thing, and for the J, we'll have I and J plus 1. So this is basically the north cell. So I have to calculate the index for I, J plus 1. So this index function will change in case of unstructured mesh. I could have written normal code, but I just kind of making it little convenient. So later we can actually replace this IDs with an array that will store connectivity matrix, etc., which we'll discuss later. Are there any questions? And then from there, everything else remains the same. So you can solve it, and the solution remains whatever we already know this before. So we have on the north, we have a heat transfer flux. So here the temperatures should reduce, and this is where we have heat generation. So it keeps on increasing as we go further and further away from the heat sink. Heat sink is basically the Robin condition that we have. East phase is actually at a lower temperature, so 300 Kelvin. So that is also having a lower value. And now you can also see there is one more problem that we kind of solved. When we were having a study heat convection equation with finite difference, we kind of had some similarity at all these nodes. At all the boundary points, we had a similarity. Now, in the finite volume formulation, we are kind of done with that. We do not have to worry about that because we are actually not solving anything at this point. We are only worried that the fluxes are only calculated at these nodes, and there we do not have any similarity. This boundary condition is completely different from them. So that similarity is completely eliminated. So we do not have to worry about that. So this is what I was saying. We do not have to worry about any singularities. They are kind of handled well with finite volume compared to finite difference method. I think there is some confusion here. Let me just do this again. So what we are trying to do is, yeah, so this is basically del T del Y is H times delta T by K. And we are trying to find the coefficient. So TB will have 2 by delta Y times K by H plus 1 T infinity, and TP will have nothing, right? 2 K by delta Y times H. Yes. And then we'll have other terms also, like we'll have the contributions from east, west, and south. So, but for now, so for the constant term, I can kind of rearrange this a little bit. So instead of writing in terms of this, I can also write this as, so 1 plus h delta y by 2 kappa plus t infinity into h delta y by 2 kappa Tp into something like this. So yeah, so if I write something like this, so basically we'll have this term. This is something that we already know, and all these values are known. This will go into the source term. This is basically the Dirichlet condition term. So this entire thing will actually go into the source term. Yeah, but the problem is we do not know the value of Tp. Because it is a mixed condition, we do not know the value of Tp. This is basically the unknown that we are solving for. So this will be the term that will go into my AP. This will be the term that will go into my B, and this will be the term that will go into my AW, the corresponding coefficient. So the coefficient is calculated here. I think I kind of little rearranged it a little bit here. Yeah, so I have taken coefficient as K times delta X by del Y. So which means the one that will be left here is the delta will be known. So this is K times L by D plus K by H. D is basically this delta Y by 2 that I was referring to. then AP will have the coefficient getting added. So this is the coefficient for the West term that is getting added into AP, and that coefficient times T infinity is a term that will get added into my source term. This is only for the boundary. For every other cell, coefficient is just A naught, which is K times delta X by delta Y, and everything else remains the same, and that will get added into the AP term. Are there any questions? Yeah, I think we still have some more time. So what we'll do now is we'll discuss something else. Now you can see this is basically what we are trying to solve now is del square T plus S equals to 0, or this is very similar to what we were doing before. Del square U is some minus F of minus F. So this is basically a Poisson equation. And here, of course, I used a direct method, but ideally, when we were starting with finite difference, we told that we can actually use a Gauss-Seidel method to solve this kind of equations. So when we are using Gauss-Seidel method, so how do we do that? Is Gauss-Seidel, you take a loop from for all the interior cells and make ui as the summation of all the neighboring cells. So half of ui minus 1 plus ui plus 1, where source term, if you assume source term to be 0, this is a simple Gauss-Seidel equation, how to solve the Gauss-Seidel. Residual is basically, you can calculate del square u value. So this is basically a Laplace equation that we are solving for here. Now what happens is, if I try to solve this, only see this first one. So initially I gave an error. So what I started out with is I considered a domain, and then I gave a particular form of equation of this particular sort, where it is u initial is some term, something like this, plus an additional term of a different frequency. And I'm trying to understand what happens to this thing. Like what I have considered is an equation where del square u is 0. This is the Laplace equation. And I have given u as 0 and all the boundaries on the left hand. Like basically I'm solving the 1D equation, and I'm saying that here it is 0, here it is 0, and try to solve for this equation, del square u equal to 0. We know that the solution is trivial, which is u equal to 0 throughout the domain. So this is a trivial solution for this problem, which we already know. So what we are doing now is, okay, let's see whether Gauss-Seidel will actually reach the solution and how fast it reaches the solution. And if it is not reaching solution, what is the reason that is actually kind of delaying this particular process? So for that, what I'm doing is, okay, the initial guess, like it is an iterative method, so we have to supply an initial guess. So the initial guess, instead of giving close to 0, I'm giving something which is a sinusoidal function, some sinusoidal function. So that is this function. So sine 2 pi x plus sine 16 pi x. So this function has two different frequencies. That is what you can see here. So this is a lower frequency which spans from 0 to 1. And then initially you have seen the higher frequency, the small ones, wiggles that you see, that is a higher frequency component, that is this 16 pi x term. So one thing you can see is those initial high frequency ones are kind of damped out initially, but this low frequency one is actually taking more time. So only see the left half of the graph. We will see we'll go to the right in little time. But the idea is these amplitudes that I have given initially are taking more time to kind of dampen out. So what we can infer from this is when we are having a Gauss-Seidel method where the errors are kind of propagating. So I have started with a shape something like this, which has two different frequencies. So these wiggles are the high frequency ones, and there is a low frequency one where low frequency is essentially from same to same. There is a large gap in the space. So for the error information to propagate, it will take much faster when these wiggles are kind of locally there. So all these local disturbances will smooth out faster than the farther ones. And these low frequency ones will actually take much longer. Whenever we have a high frequency, then it will take so long, so many iterations to actually smoothen this entire thing. So the trick now is what we do in multigrid is, instead of the frequencies, essentially how we are calculating this frequency is based on the cell size that we are considering. So if you have an elements of this, then you have to kind of travel across so many cells to say that this and this are kind of like have to be kind of dampened out. If they have to be dampened out, you have to travel across this many cells. So the idea now is, instead of doing like this, we'll actually consider a very coarse grid. Let's say we still have something like this. but I consider only a very coarse kit like this, which has only like 1, 2, 3, 4 cells. If this is 4 cells, which is basically saying that I'm only considering small subsection like this, where it has wiggles and just 4 cells, which will happen much faster. That is the main trick in multigrid. So we know that multiple frequencies of your solution will get damped at different rates using Gauss-Seidel method, and we know that the very high frequency ones can actually be dampened out faster compared to the low frequency noises. So the idea now is, okay, we know that this frequency is something that is dependent on the grid size. So what we do is we take a given grid, solve there, dampen out, smoothen out, and then we do a coarser grid. So on the coarser grid, the low frequency will actually become high frequency, and then this will be dampened out. So again, we use the smoothing, and from the coarser, you again go to the finer mesh, and from this you'll again do the smoothing, and then you'll get a solution. So the other advantage is in the coarser grid, let's say the original grid has n points, coarser grid, let's say, have only n by 2 points. So what we are doing is we are just solving for n by 2 equations. So it will be faster to solve in coarser grid also. And then once again, we can go to finer and then do the smoothing. So the total number of iterations that you actually have to do will actually get reduced. The only thing now is we need to decide how to move from coarse to fine, fine to coarse, etc. So there are different operations for that, which are not important for this particular course. But the idea I want to demonstrate here is this thing. So once you kind of handle both high and low frequency things, then it will be much faster compared to the pure Gauss-Seidel one. So this is another method to kind of solve equations. This is just to illustrate the concept of frequency that I kind of touched upon at some point in the previous week. So I just want to reiterate it here. And I'll be sharing this code on the Drive link, so you can go through this and implement it with the previous course that we already discussed. Then it will be clear for you also. If you have any questions, then we can discuss that also. Yeah, so these are the things I have for this week. To summarize, we discussed about finite volume method this week. We discussed why it is important compared to differential for arbitrary geometries, and it solves conservation by default. It involves conservation equations by default. And for a diffusion equation, we have to only worry about two kind of integrals: one the source term, the other one the diffusion term, for which we have mean value and rate approximation. Both are second order accurate. Then we discussed how to do that for a diffusion equation for steady and unsteady cases also. We discussed some of the problems, and then we saw how to implement it using a version that can be extended into unstructured, which I have not done now. Maybe in the next week, once the convection starts, we'll actually take up a little different domain instead of rectangular one. Then it will be clear to you how to kind of implement it for unstructured domains also. And then finally, we discussed about multigrid solver. The main idea here is the errors with different frequency get smoothened out differently using Gauss-Seidel method. The high frequency will get dampened out faster than a low frequency ones, and this frequency is dependent on the grid size that you are taking. So the same grid size on a coarser grid will become a higher frequency one compared to a finer grid. So the idea is you take the given grid, solve the problem on a coarser grid so that the low frequency ones in the finer grid will actually become higher frequencies, smoothen out faster, and then from there you convert it into finer grid, and then you keep doing this iteratively. So eventually you reach your solution much faster compared to pure Gauss-Seidel method. So that was the idea for this multi-grid solver. Yeah, so that is pretty much it. So next week we will discuss on convective equation. Like in addition to diffusion, we'll also have to worry about how to deal with the velocity term is already there in the picture. And then we'll discuss some problems on that, whatever problems that we solved previously. Yeah, that's it from me. Do you have any questions? Yeah, if there are no questions, then I think we can end the session for today. Thank you for joining. We may again meet next week.